I'd just like to point out that we're in the right type of room for our last talk today. Lecture hall.
Yes. And our speaker is Carla.
I want to first thank the organizers. Thanks, Frank and George, for inviting me here. It's an honor to be here to celebrate Christian's birthday. I know he's not here yet, but I'm very grateful to him for his encouragement and friendship and support through these years. I'm older than him, but he still started Partitions after he did, so it's very encouraging. So I'm going to talk about lecture hall partitions. These were introduced by Bruce K. Malou and Erickson in an article that appeared in the first issue of the Vermonology Journal. So I don't know if anybody was aware of that. I only realized that when I was preparing my talk the other night. I was looking up some background. So it's serendipitous. The lecture hall partitions are defined this way. So the lecture hall partitions of length n are sequences of n non-negative integers with the property that the ith integer divided by I is less than or equal to the I plus first integer divided by I plus 1. So you can think of them, actually, some of you tonight is probably thinking of them as the points in a cone. So each of these constraints is an inequality defining a hyperplane, and these are just the points, the lattice points that lie in the cone defined by the hyperplane. But we like to think about them as partitions, so we think of the parts, lambda i's, as being the parts of a partition of a number, and that number is the sum of the parts, the sum of the lambda i's. So the lecture hall theorem that was proved by Bruce K. Malou and Erickson is that they have a simple generating function. So you're generating them, or enumerating them according to their weight, according to the integer that they're partitioning. And the generating function is surprisingly simple for a structure that seems a little interesting, at least. Moreover, this generating function has some resemblance to the generating function involved in Euler's partition theorem. So this generating function on the right-hand side is the generating function for partitions into odd parts less than 2n. And that's a finite form of this generating function. What about the left-hand sides? Well, if you notice, the parts, I'm always used to working backwards, but if I do that, I have to start on the right-hand side. But the parts decrease as you go down from lambda n to lambda 1. They're strictly decreasing, and so the parts are distinct. Let's look at just say n equals 3. So for n equals 3, one example of a lecture hall partition would be 1, 2, 3. But the parts can be 0. So you could have 0, 2, 3. Or you could have 0, 1, 2. But you couldn't have, say, 1, 4, 5. That wouldn't work. Because 4 over 3, 4 over 2 is not less than or equal to 5 over 3. But if you chose a bigger n, like n equal 5, then 1, 4, 5 would be a lecture hall partition of length 5. And so the moral of the story here is that if you take a partition into distinct parts, it'll be a lecture hall partition for n large enough if you stick zeros on the front of it. So if you imagine taking a limit of this identity as n goes to infinity, you get Euler's partition theorem. So this is the generating function for partitions into distinct parts, and this is the generating function for partitions into odd parts. So the Lecture-Hall theorem was celebrated as a new and surprising finite form of Euler's partition theorem. It has a lot of consequences, but what I'd like to do today is focus on some things that have happened in the past 20 years connecting Lecture-Hall partitions to other things, and new extensions of the Lecture-Hall theorem. So I'm hoping that some of these will be really surprising to you. So I'm going to go through kind of quickly just to show how many different things are related to these, and how many different things come out of studying objects like these. I do want to mention, though, that there have been a lot of proofs of the Lecture-Hall theorem. I think everybody wanted to find their own proof because Lou and Ericsson's proof was elegant, but maybe it didn't really tell why. It's certainly not like Euler's partition theorem that has at least two very transparent proofs. The Lecture-Hall theorem, in spite of being proved by many people in different ways, is still fairly mysterious. But I think George has been involved in at least 3 proofs that I know of. You had an early one, and then Peter Carla and Axel Rees using... And Strail was on that using the Omega package. Then you helped Sylvia and I on a later proof of it. Alladi has I think she's been involved in 2 proofs of it, and I'm not sure, maybe I'm missing somebody. There have been lots of other proofs. Maybe you have one, but you just never showed it to anybody. Still, it's mysterious. Would you agree with that? Okay, so the first thing that you might consider, and much of what I talk about is motivated by things that Malou and Ericsson did either in that first paper or 2 subsequent papers. You might consider, what if you put different integers instead of 1 through n, s1 through sn? Will you get nice generating functions for some special s's? You wouldn't expect it to happen for all s. So let's call these S Lecture-Hall partitions. Let S be any sequence of positive integers, and look at the sequences satisfying these inequalities. Now, Malou and Ericsson only looked at S sequences S that were non-decreasing because they really wanted to have partitions. But there's no reason we have to restrict to sequences like that. For example, you could take the 5-3 Lecture-Hall partition. So here n would be 2, s1 would be 5, s2 would be 3. And we would it's still going to be a cone, and we can still count the points inside of it. It's just that they're not actually going to be partitions anymore. For example, 2-3 and 3-2 would be distinct 5-3 Lecture-Hall partitions. But we'll still, abuse the notation and call them S Lecture-Hall partitions. So for what S do we have nice generating functions? Malou and Ericsson were very interested in this question. They wondered what sequences S would give rise to generating functions of this form, and they called those sequences polynomial. And I'll show you some of their results. There are some interesting sequences that do turn out to be polynomial. One thing, though, if you don't insist on your generating function being 1 over a product, like a 1 minus q to the i's, if you just want a product, a nice product, you can take the sequence 1 through n and reverse it. So do it backwards, and you get something that we call the anti-Lecture-Hall compositions. And they have a nice generating function. And so this proof was very different from the Lecture-Hall partition theorem proof. But later, maybe 20 years later, we know that these 2 generating functions are related if we throw in an extra parameter. But I wanted to point out here that this generating function looks like it's trying to be a finite version of over partitions. So the generating function for over partitions so it's an infinite form of this. It's an infinite product in the numerator and denominator. And it includes the 1 minus q that's missing from here. So it looks like if we took an infinite form of this, that we'd get a theorem that said anti-lecture Hall compositions of any length of an integer m are equal, the number of those is equal to the number of over-partitions of m with no unoverlined 1. So did I say that right? Over partitions of M with no unoverlined 1. Over partitions are partitions in which the first copy of each part can be overlined. And so that's why you get this nice generating function in an infinite form. So it's just an observation made by looking at the generating function, but there's really no content to that observation because we didn't have a direct connection. But I wanted to mention that recently, 4 years ago, 2011, a really surprising result to me of Chen, Zhang, and Shi. So they showed if you look at anti-lecture Hall compositions of any length, but restrict the size of the last part, you get a nice product form. So the number of anti-lecture Hall compositions of n with last part less than or equal to t is the same as the number of over partitions with no unoverlined parts congruent to 0 plus or minus 1 mod t plus 2. So it's a product like it's this with another 3 terms. So that was surprising. It was still, so basically what they did is use the proof of the anti-lecture Hall theorem to connect both anti-lecture Hall compositions and over partitions to this product, to the infinite form of that product. So maybe the nicest extension of the lecture Hall theorem is to sequences that Buscemalu and Erickson called KL sequences. So they're second-order linear recurrences, but the coefficients vary depending upon even terms or odd terms. So they have initial conditions, and even terms in the sequence are L times the previous minus the one before. Odd terms in the sequence are K times the previous minus the one before. And you could let K equal L, that would be a special case. But they found that if those sequences were used in your denominator, that your generating function would have that special form, the product of 1 over 1 minus q to the i's. But even more than that, you could separately count the even indexed parts of your partition and the odd indexed parts of your partition with separate variables, and you still have a nice generating function that factors into these products 1 over 1 minus. Now it's x to a power, y to a power. And if you were in Ali's talk earlier, you see that he was counting lecture hall, he was counting partitions according to the sum of the even indexed or odd indexed parts. So this has some surprising consequences. First of all, I wanted to note that if L and K are both 2, that's just the lecture hall partitions, the original lecture hall partitions. But if you pick something strange, if you pick 4 and 1, you get a sequence that's not increasing, that's for sure. But notice it's the odd integers interleaved with the integers, 1, 2, 3, 4. If you do 1, 4 instead of 4, 1, you get something interesting. So that seems quite strange, but we're going to see there are 2 consequences of this. One is going to relate these to the little Golnitz identities, and another consequence is going to relate them to enumerating multiset permutations and sign multiset permutations. So let's see if I can give an idea. Let's skip this one. So this particular application, we're just going to look at 1, 4 and 4, 1 lecture hall partitions. Look at the generating function given by Buske, Malone, Erickson. Now you could set those all equal to Q, and if you did, you would see a finite form of the of certain products that look interesting. Now to make them look familiar, if you let x equal, if you let x equal to q and y equal to q squared and take limits as n goes to infinity, then your right-hand side products become the products involved with the little Goldman's identities. In the first case, it's partitions of n into parts from 0 into 1, 5, 6 mod 8, and in the other case, 2, 3, 7 mod 8. So what do you get on the left-hand side? In the little Goldman's identities, you have partitions with differences at least 2 and no consecutive odd parts. So here you get something quite different if you take the limit. You'll have to trust me on this if you just go back and look at those lecture hall partitions and take the limit. What you get in this case is partitions of n into distinct parts with all even indexed parts even. And in this case, all even indexed parts odd. And so it seemed like this was a one-off result because it came from a special case of lecture hall partitions, but Berkovich and Unchu just recently posted a paper to the archive in which they have a significant extension and generalization of this result. Let's see, how are we doing? So I'll show you a multi-set result. I might have time to mention, but possibly not. Let me switch gears a little bit and look at a different refinement of the lecture hall theorem that Buske, Malone, and Erickson came up with. You're still counting the original lecture hall partitions, but now you're using you're introducing another statistic, and the statistic, they call it the ceiling of lambda. It's where you take the ceiling of lambda I over I for each of your parts lambda I, and then take the weight of that. So that seems very strange, but if you look at the joint distribution of the weight and that new statistic, you get a very pretty generating function. And you get a similar thing if you get a similar result for the anti-lecture hall compositions that tells you then that there's this relationship between the two that wasn't evident before. And in investigating that relationship, we learned some surprising things. The first, in case I don't get all the way to the end, the first is that the lecture hall partitions are really related to permutations. In fact, you can interpret them in terms of permutations. And when you do, that weird statistic, the ceiling of lambda, is the Mahonian statistic. The weight of the lecture hall partition itself, when you interpret it on permutations, becomes a new quadratic permutation statistic. If you think of the major index as a linear statistic, it depends on the position of descents. The lecture hall partition is a quadratic function of the descent positions. So we get something interesting there, but in order to get there, there's a cute observation. Suppose you think about how many lecture hall partitions there are in an n-like box, just like you might ask for ordinary partitions. Well, it turns out it's a quasi-polynomial, and so to describe it nicely, we have to write k in this form, Tn plus I, and if you do that, then the number of lecture hall partitions whose last part is less than or equal to Tn plus I has a very simple form. And if you let I be 0, if you just want lambda n over n less than or equal to t, that's t plus 1 Tn. Now, if you were thinking about cones, this turns out to be an Ehrhart polynomial for a certain polytope associated with lecture hall partitions. We have I'd like to say a Q analog, but we have, Q's already get used by something else, so we have a U analog of this. If you want to count, if you want to weight this count by the statistic ceiling of lambda. Okay, so I think I'm out of time here, but let me show maybe the main thing that comes out of this. If you sum up those t's, overall t times x to the t, then you get something that's very familiar. It's McMahon's generating function. It's the joint distribution of descent and major index over permutations. And well, we can, that's essentially what we're counting here. We have to multiply by a factor of 1 minus x. But if we count lecture hall partitions according to that ceiling index and the size of the, not the size of the largest part, but the ceiling of that, then we get the descent and major index polynomial. And in that way, we relate them to permutations. And from this, so this has certain consequences. What would we do for S lecture hall partitions? Well, we can use the Earhart theory that's hidden in here to generalize to S lecture hall partitions. And what we get on this side then is a generalization of permutations in terms of inversion sequences. So you know how you can encode permutations as inversion sequences. You can use S inversion sequences to generalize permutations and get a similar result for lecture hall partitions in general. So I didn't get to tell you, I probably didn't go far enough to surprise you, but I just finished a paper about this that I'll post to the archive in the next day or two, and hopefully I whetted your appetite. Thank you very much for, let me get to the end here so I can have my thank you slide.